This video is on the Hückel rule of aromaticity. If you don't have the time to measure the heat released by hydrogenation of a compound, you can take a theoretical approach. This is to use the Hückel rule. The Hückel rule states that cyclic, fully conjugated, planar molecules with 4n plus 2 pi electrons are aromatic, where n is an integer including 0. If it does not have 4n plus 2 pi electrons, it is anti-aromatic, and if it is not cyclic or fully conjugated or planar, it is non-aromatic. You're probably wondering, what the beans, Dr. V? Let me elaborate. Here's benzene. How many pi electrons does it have? Well, there are 2 electrons in each pi bond in the double bonds. This means there are 6 pi electrons. If we make 4n plus 2 equals 6, we'll find out that n equals 1. As it ticks all the boxes required by the Hückel rule, we can say that this compound is aromatic. Let's take another one. Look at this Cyclooctatetraene. How many pi electrons does it have? Well, 2 per double bond, so there are 8 pi electrons. 4n plus 2 equals 8 will make n equal 6 over 4, or 1.5. Well, 1.5 is not an integer, making this compound anti-aromatic. We getting it? What about this compound here? Well, it's not cyclic or conjugated, and probably not planar, so therefore it is non-aromatic. If we have charges in the system, a negative charge implies 2 pi electrons, a positive charge implies 0 electrons. But recall that they can be used in resonance, so if they are involved in the cycle, they should be taken into account. Now you have a go. State whether these compounds are aromatic, anti-aromatic, or non-aromatic. You may pause now. And here are the answers. Aromatic compounds are inherently stable because of this resonance stabilization, whilst anti-aromatic compounds are very unstable, and if you have an anti-aromatic compound, it is unlikely to exist in nature. However, just because the Hückel rule states that something is anti-aromatic doesn't mean that the structure you have drawn doesn't actually exist. For example, conjugation implies planarity, but it does not mean that the compound has to be planar. So therefore, not all drawn aromatic or anti-aromatic compounds actually are aromatic or anti-aromatic. How do we know this? Well, first example, this Cyclooctatetraene is actually not a flat disk. In fact, it sits around looking something like this, making it non-aromatic as it is not planar. The third dimension is totally a thing. What about heterocycles, you may ask? Or you may ask, what the hell is a heterocycle? Well, a heterocycle is a cycle that includes an atom that is not a carbon. For example, this compound here. This is a heterocycle. Well, yes, heterocycles can also be aromatic. You just got to take into account lone pairs or charges present. For example, in this case, we have 2 pi electrons in the double bonds and the lone pair on nitrogen, which is also a pair of pi electrons, making a total of 6 electrons in this ring, meaning n equals 1, which is an integer. This compound is aromatic. What about this one here? The oxygen has 2 lone pairs. Well, if we start thinking about how those lone pairs are positioned, only one of them could be in plane with the pi orbitals. Recall that oxygen is tetrahedral with its electron domains. So when one of those lone pairs is in the plane with the p orbitals, the other one cannot be.
So when we count them, 2, 4, 6, yes, we are aromatic still. What about this compound here? Well, the lone pair on the nitrogen has been donated towards the proton. So can it be involved in resonance? No. So if that atom does not resonate and does not conjugate with the double bonds, it means that this thing is not fully conjugated, meaning that it is non-aromatic. Whilst here is the lone pair of the nitrogen involved. Think about how the electron domains are located around that nitrogen. There are 3 electron domains. They must be trigonal planar. Therefore, is that lone pair aligned with the p orbitals? The answer is no. We don't count that lone pair. So is this compound aromatic, non-aromatic, or anti-aromatic? Well, it still has 6 electrons in those double bonds. We just disregard the lone pair, giving us an aromatic compound. Now you have a go. State whether these compounds are aromatic, anti-aromatic, or non-aromatic. You may pause now. And here are the answers. To reiterate, aromaticity is a form of stability through resonance. If something is aromatic, it is more stable than expected. If something is anti-aromatic, it is much less stable than expected. What this helps with is to be able to predict things like acidity or the ability of a thing to undergo SN1 reactions, because we're looking at the stabilities of the conjugate base when it comes to acidity, or the stability of the carbocation in SN1. So for example, in this case, this compound here is going to undergo SN1 very readily because the intermediate cation is super stable because it is aromatic. The starting material, of course, is not aromatic because it's not fully conjugated. However, this compound here is never going to undergo an SN1 reaction. Why? Well, check out the carbocation. Is it aromatic or anti-aromatic? It is anti-aromatic. Therefore, it's super unstable, and therefore we cannot form it. Well, what about acidity? Well, let's remove a proton from this compound and this compound. Which one is more stable as a conjugate base? Well, this one is aromatic, this one is anti-aromatic. Therefore, there's a snowball's chance in hell to remove this proton whilst this proton is deprotonated readily. I hope that makes sense.